Dear students, hello and welcome to our interview for Lecture 3 on our series of global change. We have with us today Professor Rahmstorf, who just gave 2 fantastic lectures, and he's here to answer a few questions. So thank you very much for coming in.
My pleasure.
Okay, so to begin with, I was interested in the cyclical climate change that you showed us with the ice ages, and there have been so many and so regular. And I was wondering if you could tell me more about what causes these.
Yes, this was actually understood by a scientist called Milutin Milankovic in the 1920s, who worked out how the cycles in the orbit of the Earth around the Sun affect climate, and that they are the pacemakers of the ice ages. And so it's the tilt of the Earth axis and the direction in which it points, and also what we call the eccentricity of the Earth orbit, which change in cycles of 23,000 years, 41,000 years, 100,000 years, and 400,000 years. And in the last couple of million years, the ice ages have kind of locked into that 100,000 year periodicity, which is the dominant cycle over the last of these ice age cycles.
Okay, so there's a real, almost sort of mathematical pattern then to it.
Absolutely. I mean, we have also now succeeded in reproducing these glacial cycles in the climate model, driven only by these changes in the solar radiation received from the Earth, and we get a reasonably realistic ice age cycle, including predicting those variations in CO2, which are a major feedback in these glacial cycles.
Wow. Okay, so you can already predict maybe when the next ice age will happen.
Well, yes, actually, even the IPCC has this in its report, and because these orbital cycles can be predicted with astronomical precision millions of years in the past and into the future. And the next time when we will see a major minimum in solar radiation reaching the northern continents, which would then set off an ice age, will be in about 30,000 years from now. So nothing to worry about too much at this point.
Yeah. Okay, and you told us about how CO2 makes the ocean more acidic. I was wondering why.
Well, it's quite simple. If CO2 dissolves in water, it forms carbonic acid, which is what you have in your mineral water, fizzy water as well. And this is a mild acid.
Okay, right. You kind of discussed a bit how historians or scientists were already talking about climate change in the 19th century, and that goes quite far back. Could you maybe go into a bit more about the discussion that was going on at this period?
Yeah, sure. I mean, the basic the principles of a planetary energy balance, because it doesn't only apply to Earth, of course, it applies to Venus and Mars, etc. as well, were understood by Joseph Fourier, a French scientist who published this in 1824. And then in 1859, John Tyndall determined which gases are responsible for the greenhouse effect. That was identified by Fourier. And then in the second half of the 19th century, the major discussion amongst the scholars was what causes the ice ages. And the later Swedish Nobel laureate Svante Arrhenius, actually, before he calculated the effect of a doubling of CO2 that I mentioned in my lecture, he calculated the effect of halving the CO2 concentration in the atmosphere, because he was concerned, like most of his contemporaries, by finding the solution to the ice age problem. And he was quite right in that lowering CO2 concentration does play an important role in the ice ages as a feedback process. But it was a Swedish colleague of his who pointed out to him that he should also look at the potential effects of an increase in CO2 concentration, because already in the 19th century it was known that the emissions by human activities of CO2 started to rival the natural emissions from volcanic activity. In the meantime, of course, we are about 50 times higher in our emissions compared to what volcanoes emit in terms of CO2.
Yeah, well, that's really fascinating that already at this period they were figuring this stuff out almost by accident from being curious about the ice age. So That's very interesting. And to go back to the acidity of oceans, and we know this is a big threat to species in the oceans. But on the other hand, do you think it could lead to some species perhaps adapting to the new acidity or evolving in some way?
Well, there will be certainly some amount of adaptation, but the change being so fast makes it very likely that it will be quite detrimental to the ocean ecosystems. And in fact, we see examples of that in the Earth history. In the last 300 million years, there have been several incidents of ocean acidification for some natural reasons. The major, quite fast one happened about 55 million years ago, which caused a major mass extinction amongst these calcifying organisms in the ocean who basically sank to the bottom and dissolved their shells, and they formed a mud layer that you can still find. And it's estimated that about half of the species of these beautiful foraminifera that I showed some microscopic shells in my talk went extinct during that episode. But even that episode of acidification went much slower than what we are causing now. So the rapidity with which we increase the acid content in the oceans is unparalleled by far over the last 300 million years.
Mm-hmm. So in short, there would be no time for any species to adapt or evolve because they won't have the chance.
Well, you know, there is some adaptation, but certainly it will not be an adaptation that leaves basically the ecosystems intact as we know them, but rather there is a great risk that we will lose most of the coral reefs, if not all of them, for example.
Yeah, which makes this issue even more pressing. And you mentioned CO2 as a greenhouse gas and the fact that there are some other gases. So which gases are these?
Well, there's, for example, methane, nitrous oxide, and the CFCs, which are also have been known to cause the ozone hole. So chlorofluorocarbon CFCs are now highly regulated simply to protect the ozone layer. But at the same time, that also helps the climate because CFCs are also a global warming agent.
Okay, yeah. And, you know, there's all this discussion about climate change caused by humans compared to natural causes. But what kind of natural causes could actually cause the Earth to warm?
Well, as it happens, if you look at the last 50 years, the natural effects have had a net cooling effect. The main reason for that is that the luminosity of the sun has declined somewhat. So the sun is quite weak now, but this is not a major point. This is offset only a very small portion of the global warming caused by the increase in greenhouse gases. I mean, there are people who discuss exotic effects like maybe cosmic rays influencing our climate by affecting cloud cover. But if you look at the measurements of cosmic ray incidents that have been ongoing since the middle of the 20th century, we also see no trend in cosmic rays reaching the Earth. So even if they had some effect on cloud cover in climate, at best they would produce an 11-year cycle, because the cosmic rays fluctuate in the same 11-year cycle as the solar activity does, because it's actually the solar activity that modulates the influx of cosmic rays on the Earth. And there is another very strong piece of evidence that the cosmic rays don't have a big effect, and that is if you look at the impact that the 11-year cycle has on global temperature. You can find that out by a simple correlation analysis that I showed in my lecture. Then you see that the effect is just as large as you expect from the changes, the measured changes in the solar luminosity, so the brightness of the sun. And that doesn't leave any room for some as yet physically unexplained additional effect, certainly not a large one.
Yes. So basically the effect that humans are having on warming the climate is unparalleled.
Well, it's the human effect with which is easily calculated, the CO2 effect alone is 1.7 watts per square meter, and that already is 10 times larger even than the kind of peak to valley changes in this 11-year cycle of the sun, let alone the long-term trend in the solar activity. So it's very clear that if you look at the cause of global warming, you have to look at where does the heat come from. It's the first law of thermodynamics, the conservation of heat. And so you have to look at the planetary energy balance, and that's measured by satellites, and humans are clearly the by far dominant reason for changes in this radiation balance.
Yeah, so the evidence is pretty undeniable there.
Well, that's why practically all climatologists agree on this point. I mean, there are various surveys have been done that show that 97 to 98% of climatologists are convinced that humans are changing the climate.
Yeah, yeah. We just need to convince everyone else. And then this question might be difficult to answer, but I think what a lot of people think about are the effects that could happen if the global temperature did in fact rise by 7 degrees. And like, can you already think of some things that might happen to the Earth if that were the case?
Well, if we allowed this amount of warming to happen, we would certainly steer the Earth into really uncharted waters, uncharted for many millions of years. If you look back in time, the last time it was significantly warmer than now was about 2 or 3 million years ago in the Pliocene, and that was only about 2 degrees warmer on global average than now. Or if you go back even further in time, 40 million years ago to the Eocene, for example, there we're talking about maybe 3 or 4 degrees warmer temperatures, but that was a world that was free of ice sheets, for example, so sea level was 70 meters higher. That is about, that's the amount of ice that we have today on the planet. If we melted down all the ice in Antarctica and Greenland, and the mountain glaciers just make a small contribution, but you would raise sea level by 70 meters roughly.
Wow, would there be any land left in that case?
Well, sure. I mean, there's obviously a lot of mountain ranges, but this would destroy practically all the coastal cities that we have built. If you just look back at the last ice age, 20,000 years ago, quite recent really, that was a planet that was about 4 to 7 degrees colder in global average than today. And that was a completely different world. For example, the sea level was 120 meters lower 20,000 years ago. And then when this warming out of the ice age happened, of those 4 to 7 degrees, 2/3 of the ice masses back then were lost. That raised sea level by 120 meters, and so we have 1/3 of the ice left. So think what happens if we warm the planet by another 4 to 7 degrees. How much ice will we lose of those remaining 70 meters worth of ice that we have now? I'm sure it's going to be more than a few percent, and already that will have major impacts on our coasts.
Yeah. Okay, so in short, less ice, more water. And that kind of brings me on, what you've been saying brings me on to your second lecture, and these heat waves that have been occurring that seem quite drastic, really, and yet we say that the Earth, is only a couple of degrees, there's only a couple of degrees difference, and we think, 15 degrees isn't very different to 17 degrees, so why are we seeing such drastic changes already?
Well, we have seen about a bit less than 1 degree centigrade of warming since the late 19th century, and that would sound little to a layperson, I'm sure, given the huge differences we have between winter and summer, for example. But you have to remember it's a global average, so most of the global average is made up by the air over the oceans, which have warmed less, so the land temperatures already have warmed more than that. And of course you have large regional differences. And if you do the statistics properly about those monthly heat records, then indeed what you would expect after about a bit less than 1 degree global warming, the increase you would expect in the heat records is nicely explained by that. So it's just this 5-fold increase in monthly heat records is totally consistent with a warming that has only been about 0.8 degrees centigrade. It might sound surprising to lay people, but if you do the analysis, that's what you get.
But it's important in taking it seriously that, you know, the small amount of warming can cause these drastic effects.
Yeah, I mean, you see very clearly how much it can do to sea level based on past experience, the historic experience with ice ages, etc., that a few degrees warming can cause tens of meters of sea level rise in the long run. And you may also expect major changes in weather patterns because, for example, the water cycle is enhanced, so you get more evaporation from the oceans. In global average, you get more rainfall. But you also have the phenomenon that the rainfall tends to concentrate in shorter term, very large rainfall events, which cause flooding and then interrupted by longer periods of drought conditions. That's a peculiar effect of the water cycle that is, of course, not very good for humans. Yeah. You also get seasonal changes, for example, where I live in eastern Germany, we get little change in the rainfall over the year, but we get more rain in winter and less in summer. And of course, in the growing season in summer, that's when the farmers need the rain.
Yeah, so what causes these drastic changes? Because as you say, I've also experienced this too from my country, that there's a lot more rain in winter and drier summers. So why is it this, you know, contrast of rain and drought?
Well, that's not completely understood why the regional changes are so different, and the seasonal changes are also not the same everywhere. It depends on where you look. But there are some robust features of the precipitation changes, and that's this general enhancement of the water cycle, which makes the already wet areas even wetter and already dry areas even drier. The dry areas of the planet are associated with downward moving air, and the wet areas, they tend to be associated with rising air masses, like in the tropical rainfall belt. And if you enhance this circulation and you get a stronger downward moving air over the desert and semi-arid regions, then these will get even drier than they already are, like we find in the Mediterranean or South Africa, for example.
Okay. And this has big effects on, you know, crop growing and things like that, I would imagine.
Sure, that has a major impact on farming and food security. And there's also studies that look at the impact of global warming on agriculture, on food supply overall. And they find that if you manage to limit the warming to about 2 degrees, then overall it might even enhance the agricultural productivity worldwide, although the tropics tend to be the losers and the higher latitudes the winners in this game, which raises some real ethical and distribution issues and food security issues for the tropical regions of the world. But if you go beyond 2-degree warming, then even the overall global agricultural productivity starts to decline as the negative effects of global warming then kick in.
Mm-hmm. Okay. I found it very alarming when you were talking about these ice sheets in Greenland, I think, and the fact there was this tipping point where if it gets past that point, even if we manage to mitigate climate change, the ice will continue melting. Are there any more examples of this, maybe?
Yes, I mean, this is a big discussion in climate science, the so-called tipping elements of the climate system, where the changes don't occur in a gradual and slow and linear manner, but where you reach thresholds where some rapid change happens, like, for example, think of a rowing boat. If you tilt it a little back and forth, it's practically linear, but if you tilt it too much, it will tip over. And that's where this kind of image of a tipping point comes from. There are many examples of potential tipping points in the climate system. I mentioned the Greenland ice sheet. There is a risk of major changes in ocean circulation, especially in the North Atlantic current. There is a risk of releasing methane, a powerful greenhouse gas that could be released due to warming, either from so-called hydrates at the seafloor, which is a kind of metastable form of methane in a kind of icy form together with seawater, or methane that is now locked up in permafrost areas on land, and when they heat up and melt the permafrost areas, that will also release methane. And things like that will mean basically a loss of control for humanity about the climate system, because then things start to change by themselves without us being able to stop them anymore.
Okay, and that's why we need these guardrails so that we can still do something about it then at this point.
That's true. I mean, one of the rationales behind limiting global warming to 2 degrees has been in the past that it was thought, that's in the last IPCC report, that the risk of Greenland going beyond that tipping point starts at about 2-degree global warming. Unfortunately, more recent studies show that it's actually quite likely that this threshold is below the 2-degree warming limit, so that probably limiting global warming to 2 degrees will not be enough to prevent the meltdown of the Greenland ice sheet. Of course, I should add that it's because the ice responds quite slowly, we could afford going above this threshold for maybe 50 or even 100 years, as long as we then manage to get the temperatures back down again. But unfortunately, there's no real proven way of how we could reduce the global temperature again. For that, we would have to actively remove CO2 out of the atmosphere because of its long lifetime. It doesn't go away by itself fast enough.
Yeah, and as you said, the only safe option is zero carbon.
Well, zero emissions and possibly even negative emissions, which turn up in some of the scenarios, and they could be achieved by growing bioenergy plantations, and then when you burn the bioenergy, I hesitate to say biofuel, because turning biomass into a liquid fuel is not a very good idea, but it's better to burn solids, wood for example. You can burn wood in a power station, and then capture the CO2 that is emitted while you burn it. So in that way you could create negative emissions, because the plants, they remove CO2 from the atmosphere through their photosynthesis. If you then capture the carbon that is released when you burn the plants, then you have negative emissions. But of course the problem is, do we have enough land for major bioenergy plantations if we need to also feed a growing world population?
Yes, of course. That would almost be the next step, because like our current goal is already quite ambitious, I suppose. So, and just to go on, I found this really great what you're doing in North Carolina in these salt marshes, and finding out about the ancient sea level. Is there a certain reason why you chose to do that in this certain area in North Carolina?
Yes, our project colleagues, mainly Ben Horton and Andy Kemp, they found this spot there, which is particularly good because it is situated on what we call a glacial forebulge. That is a piece of land that was pushed up by the glaciers in the last ice age, because the glaciers, they actually depress the land where they sit. Under the glaciers get pushed down, but just around the glaciers a little forebulge gets pushed up. And now, because the glaciers went away again about 10,000 years ago at the end of the last ice age, this land is now moving back down. So it's sinking land, and that means that relative to that land, the sea level is coming up continuously. And so that means that a continuous buildup of sediments occurs in those salt marshes, and that is a condition to get a continuous record of sea level rise. And then in the end, of course, you have to subtract that land movement out to get the sea level rise proper.
Okay, so because of all these sediments, you can have really clear evidence and see very clearly what's been going on.
That's right. I mean, using sediment cores for paleoclimate studies is a very well-established technique that has been used for many different types of data in different locations.
Yes, and going back to these heat waves that we've been seeing, is there also a chance of seeing cold weather due to global warming?
Well, I would say the overall picture worldwide is that the probability of getting cold months is decreasing and the probability of getting hot months is increasing. But there are some regional specialties where this could be different, or actually is different. And those are particularly areas where you get cold snaps due to the the movement of cold air masses from the Arctic, for example. And there is a paradoxical effect, especially in Europe, that the loss of sea ice in the Arctic Ocean actually increases the chances of a high-pressure system forming over the Barents Sea, which was formerly ice-covered and now tends to be partly open. And this high pressure steers Arctic cold air into Europe and leads to cold snaps like we saw in the winter of in February 2012, where we had an extreme cold snap which broke even some cold records. And this in no way contradicts global warming, but is an effect that actually was predicted by model simulations before this cold snap happened, and was published in the scientific literature as a mechanism that we find in the climate models, and that is now borne out by reality as well.
Okay, so in general you expect to see more warm weather, but you can have these exceptions.
That's right.
Mm-hmm. I was interested about the sea ice because I gather that they contain less salt than seawater, so when they melt I would expect the sea to be less salty, and I was wondering if that were true, and if so, would this cause any effects?
Yeah, that is first of all true. It is a part of the dynamics of the system of sea ice formation that the salt gets left behind. We call that brine rejection. It has some impact on ocean circulation. An even bigger impact is the meltwater that comes from the land ice, not the sea ice, because the land ice, like Greenland, that has no salt in it because it's formed by snow falling on the continent and not by freezing seawater. And that tends to dilute the surface waters of the ocean, so they get less salty. That is actually the mechanism behind one of the tipping points, namely the North Atlantic current. If that gets pushed across a threshold where it collapses, as some model scenarios suggest, there is a small risk of this happening, then it would be because of a large meltwater input from the Greenland ice sheet.
Okay, well, that's very interesting. And then I guess one of my last questions, we already know that the sea level has risen by 20 centimeters, 20 centimeters or so. Does this already have any effects? Because we know that we can lose land if it goes up a few meters, but does it have any effects at this kind of relatively low level?
It probably has an effect. First of all, if you have a higher sea level, it tends to enhance erosion rates, coastal erosion. And secondly, if you have a higher sea level and a storm surge hits, then this storm surge will also run up somewhat higher. Typically, if you have 20 centimeter higher sea level, to first order, you would think the storm surge also runs up 20 centimeters higher. There are some nonlinear effects that can add to that, so the storm surge levels end up being elevated even more than the mean sea level. But this would be difficult to detect in measurements from the past because, storm surge statistics wouldn't really show any effects yet, because storm surges are extremely variable in height and quite rare events, and to do proper statistics where you could detect a 20 centimeter change, you would have to have a huge number of events. So I would say physical logic argues that yes, there is an effect that makes the storm surges a little bit worse, but it's not large enough to detect in the storm surge data yet.
Okay, so it's not a good thing at any rate. Yes, and just finally, I just wanted to ask you kind of your opinion on whether, how positive you are that we can reach this 2% limit by 2 degree limit by 2050.
Well, I hope that in the report that we published, that this whole lecture series is about, we show that it is entirely feasible, both technologically, also economically, to keep the warming below 2 degrees. Actually costs a tiny fraction of GDP to do that. And even a more stringent limit of 1.5 degree, in my view, would be sensible. It's all simply a matter of cost. And I think it would be difficult if our children or grandchildren ask us, why didn't you save the world from this? And we say, well, it seemed too expensive to us.
Absolutely. And of course, it would be more expensive to deal with the consequences later.
Well, that's what the economic studies tend to show, that not doing something against global warming will turn out far more expensive. Of course, actually estimating the damages that would be caused by climate change, that is a very uncertain business, one has to say. So I don't think we really can estimate the damage costs of climate change. But we can estimate reasonably well how much it would cost to reduce our emissions, because this is all with known technologies. We know how solar power works, how wind power works, what it costs, how the costs go down with experience and learning curves, etc. So these cost estimates are on far more solid ground than the kind of uncharted waters that we move into if we let climate change simply happen.
That's very important. And this has been very fascinating to go into more detail on your lecture slides, and it was really great talking to you, and I really hope that our students also gained a lot from this too. And that was it, so thank you very much.
Thank you very much.